Okay, let's review linear programming by doing some problem sets. And here in the first problem set, you already see three constraints, and the resources that are constrained, they are used in order to produce guns and butter. So that's the classical example from economics for the production possibility frontier. And so a country can produce two goods, guns and butter, and consumers value butter twice as much as guns. So that basically means that the price of butter is twice as high than the price of guns. And guns and butter are produced with the three production factors: land and machines and workers, actually three production factors. And the following table summarizes the input. So in this, we essentially have a production function. We want to maximize maybe something like GDP, max. I call it GDP, and economists like to write that as Y. And then we have the price of butter times butter plus the price of guns times guns. So that would be essentially the formula for GDP if there's only guns and butter being produced. And that is subject to the constraints. So the constraints are that land. So the production of guns produces no land but one butter. So now the land constraint can be written as, so we have, what was it? Okay, so no, so the production of gun reduces, so it's 0, it's one butter. So for any butter that we produce, we need 1 unit of land, but 0 guns. So that's 0, and we have a total of 9 units of land. And the machines we need for the production of machines, one machine requires 3 guns and 3 butter and 2 butter. So that is 2 butter plus 3 times guns, and that is less than or equal to 30. And then the final constraint is the workers. And we have a total of 44. And the production of each requires 4. So we can write 4 for butter plus 4 for each gun. And we have less than 44. Okay, so this would be the problem formalized. And now let's see what the first question is. The land constraint is represented by which line? Okay, so land is obviously the blue line, because if I use up all my resources to produce butter, I can produce a maximum of 9. So A must be butter, and there is no trade-off. That's why it's a horizontal line. So I theoretically could produce, given the land constraint, an infinite amount of guns, because I don't need any land for the production of guns. So the land constraint is represented by A. The workers constraint, okay, I have 44 workers. If you used up all your workers to produce butter, then I could produce 11 units of butter, because 44 divided by 11. And if you used up all your resources to produce guns, then I could also produce 11 guns with 44 workers. So C, which is the green line, That is the workers constraint. And the machines constraint, well, that should be then B. But let's double check. So we have 30 machines. If you use up all your machines to produce guns, I could produce 30 over 3, so that's 10. And if I use up all my 30 machines to produce butter, 30 divided by 2, that's 15. Okay. So now mathematically, the land constraint can be written as B equals 9. So, because on the intercept, we have only an intercept, we have no slope, the slope is 0, so B equals 9. Then the next question is, mathematically, the workers constraint can be written as, well, that is B 11 minus 1 times. It starts at 11 and it goes till 11, so the slope is -1. And of course that should be not F, but G. On the keyboard the F is right next to the G. So that should be this. But the point is that, yeah, I have to change this. It's a typo, it's all G's. And here also. G. And mathematically, the machines constraint can be written as, so that is, it starts at 15, and the slope is, the rise is 15, over the run is 10, so 15 over 10, so that's minus 1.5. So that must be B. Which of the following production combination is both feasible and efficient? And again, something that's feasible is either inside or on the frontier of the area of feasible production. And if it is efficient, it is on the frontier of the feasible production. So we have 9 and 2, for example. So 9 and 2 would be here, and that is clearly feasible because the area of feasible production goes from 9 to 2, and then we go on the green line, and then we, as soon as we cut the orange, we go to the orange line. So that is both feasible and efficient. So B equals 9 is feasible and efficient. Which would be inefficient? Well, it must be something inside, probably the 4 and 4. So let's double check. Yeah, 4 and 4, that would be inside the PPF. So that means with my given resources, I still could produce more of both guns and butter. I don't face any trade-off. So that can't be efficient. So that must be some resources are slacking off. So for example, in order to produce 4 units of butter and 4 units of guns, you see that then I need basically 4 times 4, 16 workers to produce guns and 16 workers for butter. So 32 workers are only working. Well, I have some, that means I have some 12 workers that are unemployed or are slacking off that can be still used. So which of the following production combinations is inefficient? That is inside. And which of the following production combinations is not feasible? Well, that's probably the 6 and 6 that should be outside the PPF. So let's double check. So 6 and 6, yeah, even though it is on the orange one, but it's beyond the green one, so it's outside the area of feasible production. And again, the area of feasible production would be everything inside here. So that would be the area of feasible production. And that's a little bit too high here, but you get and so that would be outside the green constraint. So okay, so if a unit of butter sells for 4 and a unit of guns sells for 2, so butter is twice as valuable, then what would be the iso profit function look like for y equals 32? Okay, so we say then y equals 4 times b plus 2 times guns. That's the general formula. So now we want to rearrange this formula to fit our graph where we have b on the y-axis and guns on the x-axis. So we need an iso profit line that looks something like this. So let's rearrange this term for b, and then we can write for b equals y minus 2 times g, and then we divide both sides by b, and then we get b equals y over 4 minus 2 over 4. So that's the price of guns over the price of butter, so minus 1/2 times g. So that would be it. And now we can insert the 32 for y, and then we get 8 minus 1/2. And there's again the must have missed. Okay, so this is 8, because if we plug in for y38, we get 8 minus 1/2 g. Okay, so now how do we determine the optimum? So graphically we need an arbitrary iso profit line like the one for a profit of 32, and it has a slope of negative 1/2. So what matters is the slope. So let me insert here something with a slope of negative 1/2, like something that goes from 4 to 8. Okay. And let's make it dashed like always for the iso profit line. And then what we do is we want to shift it as far out as we can from the origin, so that we still find the point of tangency with the area feasible production. You can see the furthest you can shift it from the origin is indeed where we get the intersection at 9 and 2. Okay, so that should be the optimum. So that should be the optimum, and that means at the optimum 9 and 2, so we have butter 9 and guns 2. And how big is the social profit? Well, that is 9 times 4, 36, plus 2 times 2, so that is 40. Okay, so that's it, and so we have derived the solution graphically, but let's also quickly program that in Excel. And so we always start with the decision variables. And we have guns, and we have butter. Okay, so then we have the optimum values. That is what Excel will decide. And then we need we call it unit profit or unit social benefit. Call it unit benefit to society maybe. And we said that butter is twice as valuable. So we put in here 2 and 4. And for these cells that Excel will choose, I just put in a 0. And let me make that a little bit bigger. Okay, so then we have the constraints. And we have guns and butter. And we have the 3 constraints: land, machines, and workers. Okay, now let's format it a little bit nicely. Okay, so now I can just copy the production coefficients 0, 3, 4, and 1, 2, 4, 1, 2, 4. Then we need the total usage. Okay, then we add the sign. And then we have a column for the available. And so we have 9 units of land, 30, 44. The sign is always less than or equal. And now I still need to enter some formula. So let's first highlight the cell. So this was an input cell. So we had to input some data that is given. And that is given. And those are given. So the total usage needs to be calculated from the calculation that Excel will do. So I say this is maybe a output. Excel will output what the optimum quantity is. Then I still need the maximum, let's say GDP, Y. Okay. And now I use again the formula sum product. So this is equal to the sum product. Okay, so I highlight the first array, comma, then I highlight the second array. And so what Excel will do, 0 times 2 plus 0 times 4. And you can see if I add here 1, it changes to 2, and if I add here another 2, it adds to 10. And this is a calculation. So let's highlight it as a calculation. But then I need 3 more calculations for the total usage. So that is equal to, and again, sum product. And I take this, but now because I want to copy down that formula, I fix that. And the second one is the coefficients for the land constraints when producing guns and butter. And now I should be able to copy that down. And again, this is also a calculation, and this is how we need to set it up in Excel. And so now if we run it, we should actually get the result 9 and 2. But I initialize everything again to 0 first. And then we go to data, and then solver. Okay, so I want to maximize GDP, which is in my case cell E3, by changing cell C3 and D3. subject to the constraint, we add. And now again I can use the shortcut because those sides are all the same. I can just drop and drag it down, and then for the constraint, okay. Then we want to make the unconstrained variables non-negative, and we use simplex. And now when I press solve, we should see the same as here to the left in the graph from the problem set. So solve, and we get the same result, 9 and 2. And this is what it looks like. So yeah, so let's just stop here, and then let's continue with a couple of more problem sets in the next video. So I'll just stop here.